Hello my dear students of B.Sc 6th. Today I am going to take a discussion on the molecular spectroscopy. I am Mr. Anand, working as Assistant Professor in Chemistry at ADB First Grade College, Arukunadi. When you come to the video lecture series of the molecular spectroscopy, now we are going to take a discussion on the rotational spectroscopy or a microwave spectroscopy. But before going to that spectroscopy, just I recall you what I discussed in the previous video. As you know, the spectroscopy is nothing but an interaction of the electromagnetic radiations with the matter. And as you know, this electromagnetic spectrum consists number of regions varying from radio waves, microwaves, infrared, visible, ultraviolet, X-ray and gamma rays. Depends on the type of radiations which interact with the matter, it causes a different changes in the molecule. If the radius interact with the matter, it causes changes in nuclear and electron spin. Whereas the microwave causes molecular rotations. Infrared radiations causes molecular vibrations. Visible radiations causes the changes or transition of outer shell electrons. Ultraviolet region causes a molecular dissociation. X-ray causes a transition of inner shell electrons, whereas gamma rays causes a nuclear transition. Like this, there are the different changes that occurs when the EMR interact matter, but we are mainly consider two important types as a rotational vibration and a combination of rotational vibration. And today we shall go for the discussion on the mainly the rotation spectroscopy, or it is also called microwave spectroscopy. Hello my dear students, welcome to next video, that is a molecular spectroscopy part 2, rotation spectroscopy. Now let us going to discuss these topics in this coming video. Theory of rotation spectroscopy, rotational energy levels, transitional rotation spectrum, selection rule, intensity of spectral lines and applications. See, when you come to the first type of spectroscopy, the rotational spectroscopy, or it is also called a microwave spectroscopy. It is the simplest type of spectroscopy. It deals with the study of interaction of microwave radiation with the polar molecules, causes the transition between the rotation levels. Rotation spectroscopy is concerned with the measurement of energies of transitions between quantized rotational state of molecules in the gaseous phase. It accomplishes this through the interaction of electric dipole moment of the molecules with the electric field of the existing microwave photon. That is, we can say like this: microwave theory deals with the pure rotation motion of molecules, and the condition for observing resonance in that region is that molecule must possess a permanent dipole moment. When a molecule having a dipole moment rotates, and it generates an electric field which can interact with the electric component of the microwave radiations. During the interaction, the energy can be absorbed or emitted, and then rotation of the molecule gives rise to spectrum. See, the minimum and necessary condition to cause a rotation in a molecule when the electromagnetic radiations interact with the molecule, that is, the molecule must possess a dipole, means it must have the permanent dipole moment. As you know, already well familiar with the molecular structure chapter, dipole moment is nothing but a magnitude which refers the polarity of the molecule. Mu is equal to R into Q. And if it possesses a dipole moment, such type of molecules only they do show rotation spectroscopy, or it gives a rotation spectrum. When you say the word dipole, means they have the two poles, plus and minus. When you consider a molecule with a heteroatom, which have the different electronegativity, and they have the difference in electronegativity, they have the difference in electron attracting tendency. So one end causes a negative charge or a partial negative charge, and the other end causes a positive charge. So because of this distortion, that means there is the electron density between the two atoms going to changes. Now those which have the more electronegative, they get the partial negative character, and where that is the other atom gets a partial positive, then it is said to be a dipolar molecule. When such type of molecules only, they do show the rotation spectroscopy. Now when you look at this, when the molecule going to absorb microwave radiations, an electromagnetic wave is an oscillating electric field and interact with a molecule that can undergo changes in dipole moment. The oscillating dipole can be provided by the rotation of permanent dipole, like example HCl. This type of interaction leads the microwave spectra. See, when the molecule having a dipole, means that has a plus and minus, and that molecule undergo rotation. When it undergo rotation, now what happens during rotation of a dipole molecule, an electric field is generated to rotations. When the frequency of the electric field of the dipole moment, when it compensates, that means when you compare this electric component of electromagnetic radiations, when those two are equal, means electromagnetic radiations of electric component of electromagnetic radiations and the electric field of the dipole molecule, when they get equalized, then in such cases the molecule absorbs micro radiation, then it starts a rotation. When it undergo rotation, this is the type of rotation what you observe. This is a type of molecule, it's a dipole. This is representation of the dipole moment. When it starts rotating, this is a rotation. Now it rotates like this, is a rotation, this is a rotation. Again this under rotation, and this under rotation, and also under rotation. So this type of rotation causes the change the dipole moment, and when the dipole moment changes, now during the change dipole moment, we can see the interaction of the microwaves of electromagnetic spectrum and causes the electromagnetic spectrum in that molecule. So this is how we can represent rotation of the dipole molecule take place now, and this type of the way the electric field is generated to rotation, and this electric component of dipole moment, when it matches with the electric component of electromagnetic radiations, then it absorbs a micro radiation, then it causes changes in the rotation of the molecule. So thus we can see the microwave radiation causes rotation of the molecule. This spectroscope utilizes the photons in the micro range to cause a transition between the quantum rotation energy levels of a gas molecule. The reason why the sample must be in a gaseous phase is due to the intermolecular interaction hindering rotations in the liquid and solid phase of the molecule. See why the reacting molecule must be in a gaseous form, because in case of a gaseous form, they have the more freedom of rotation, they are free to rotate. But in case of solid and liquid, the molecules are getting intermolecular force of attraction. There is no free rotation for that molecule. Therefore, the molecules in a solid state or liquid, they do not show this interaction with the microradiations. Therefore, it is not shown by these solid and liquid substances. As I told you, that we have the two types of molecules, non-polar molecules and polar molecules. So non-polar molecules, homodiatomic molecules, do not have the dipole moment. Therefore, they do not give microspectrum, and these are called microwave inactive molecules. Example, H2, N2, O2, CO2, etc. And these, since the two atoms of the molecules are same and they have equally electronegative, there is no any distortion or disturbance in the electric field, that is electron density between the two atoms. It lies exactly between these two, so there is no chances of getting a plus or minus in the molecule. But in case of a molecule with a heteroatomic atom, the molecules have the dipole moment, so they give microspectrum. These are called microactive molecule. HCl, HF, CSCl, H2O, CSCl. All these molecules are said to be heteroatomic molecule, and these are called microwave active molecules. And because of this reason, all the molecular possess a polarity because of difference electronegativity of the two atoms in this one. It causes the microspectrum. Rotation about each unique axis is associated with a set of quantized energy levels dependent on the moment of inertia about that axis and the quantum number. When molecules under rotation, we have angular momentum. Angular momentum is equal to I into omega, where I is called moment of inertia and omega is called angular velocity. Now let us go for the understanding what is meant by moment of inertia. Moment of inertia is a quantity expressing a body's tendency to resist the angular acceleration. Or we can also say the amount of torque, that means amount of force required to rotate a body or accelerate the rotation. It is also called mass moment of inertia, which is a measure of an object's resistance to change in its rotation rate, or it is the rotational analog of mass. Now let us consider this is a dipole molecule. Observing this in the video, this is a dipole molecule, and these two atoms are of different kind. And when this molecule under rotation, see, just observe this, what in the on this screen we can see there's a presence of two dipole molecule. Red is one atom and another is a gray is another atom, and these two atoms are present in the molecule having a dipole. When it under rotation, then you must have certain center of gravity. This is a center of gravity, and from the center of gravity, what happens? This molecule start rotating. When you this is a molecule, now it start rotating. That means when it causes rotation, we have to apply certain force. We have to apply certain force. The force which is applied on the atom or a molecule to cause a rotation, so that is called a moment of inertia. Or we can also say this body can oppose the force which is acting on the body to cause a rotation. That's what you can say, a quantity expressing the body's tendency to resist angular acceleration. If I apply certain force now, and this molecule it causes the force opposes now the tendency of that atom to cause resistance of acceleration, that is called moment of inertia. Or the force which required, that's the amount of force, amount of torque required to rotate a body or accelerate this one. So how much amount of force is applied on this side to cause the rotation, and that is nothing but a moment of inertia. The moment of inertia is nothing but the amount of torque required to rotate a body or acceleration. That's called moment of inertia. So moment of inertia plays very important role in study of the micro radiations. Okay. Now when you go for the study of the molecule in 3 dimensions, when that molecule has a different type of moment of inertia in a different axis. So based on the angular, that is based on the shape of the molecule and their moment of inertia around their 3 orthogonal rotational axes or a 3 dimension, molecules are broadly classified into 4 types: linear molecules or a diatomic molecule, spherical tops, symmetrical tops, and asymmetrical tops. But we are mainly concerned the study of there's a linear or diatomic molecule, but remaining are not concerned ourselves. But anyhow, so this type of examples may be asked in the next set or net computations. That's why I mentioned all the 4 types, but we are mainly concerned study of the linear molecules or diatomic one, but they are in 3 dimensions. Let me take this, a molecule can have the 3 different moment of inertia, IA, IB and IC, according to the axis of rotation. Let us understand when you call that molecules a linear or diatomic molecule based on the moment of inertia of that molecule on the 3 axes. Now let us consider this is one axis, this is x-axis, and here now this is a principal axis, and this now here this is a y-axis and z-axis IB, and this is a y-axis and z-axis. Now there may be a certain center of gravity or a center of mass. From the center of mass we have the rotations. Now when you observe this one, this is a principal axis. Now the molecule under rotation, and this molecule under rotation three axis. One is x-axis, y-axis, z-axis here. Let us consider a molecule in a principal axis, the x-axis. Say this is a x-axis. This is a principal. Now let us have there is a center of gravity in this one. Now when you have this rotation like this is a molecule. Now you can rotate the molecule in this direction. See, along the axis, the principal axis. This is the principal axis. See this rotation. Okay, this is a rotation. This is one way of rotating the molecule in the principal axis. And another way rotating, we can also rotate like this. We can rotate like this. Is also rotation. This is also the molecule can also rotate here, and the molecule can also rotate like this. So because of these three type of rotation, it causes a different moment of inertia on all the three axes. See, in case of this principal axis here, so when you go for rotating the molecule along this principal axis, see, we have to apply certain force to cause the rotation of the molecule on the principal axis. When you observe this rotation, there is no change the position, the relative position of atoms. The position of atoms remains same. The position of atoms remains same, but there is no change the position of atoms in the molecule. Therefore, very less amount of force is required to cause the rotation. So very negligible. Therefore, the moment of inertia along the principal axis IA is taken to be 0. Not exactly 0, it is almost equal to 0. That's what IA is equal to 0. Now, when you take this another rotation, other axis, suppose if you rotate this molecule like this in this direction, this is a direction of motion. So this is a direction of motion. When you observe and rotate the molecule, what happens? We have to apply certain force to cause this rotation. But here, the position of the atoms in the molecule changes. Because it's in the position of the atom in the molecule, that causes changes in the the dipole moment. Therefore, this IA is to be taken as certain moment. Similarly, we can also rotate like this. Is a rotation, another rotation. This is a rotation of this one, and this also causes the change the moment of inertia, and also we can see certain amount of dipole moment also changes. And this is what is a moment of inertia along this axis. And moment of inertia along this axis are found to be same. We are now IA is equal to 0, IB is equal to IC. So this is a condition. Say the molecule is said to be linear diatomic if IA is equal to 0, if IB is equal to IC. Now such type of molecule is said to be linear diatomic molecule. This is how we can say. The same thing I just drawn here. This HCl. Let us take HCl example. H is having a positive and negative here, and it under different type of rotations. Therefore, I is equal along this axis. When you rotate this, along I is equal to 0, IB is equal to IC. Now, next one is a symmetric top molecule. This is what is a fluorine, and here the other three atoms are hydrogen. So, we are taking this as a center of gravity in this position. And here now, when you go for the study of the what is the change, the moment of inertia on all the three axes, you can see IB is equal to IC, and which is not equal to IA. But IA is not equal to 0 because you have to apply certain amount of the force to rotate this from the fluorine atom. So it has certain amount of moment of inertia required. Therefore, IA is not equal to 0, but IB is equal to IC. So such type of molecules are symmetric top molecule, and a spherical top molecules. So when you consider this is a methane molecule, and here the C being a center of gravity, and all the bonds are equal. Therefore, when you observe this, what is the moment of inertia in all the three axes? IA is equal to IB, IB is equal to IC. Therefore, this is said to be the no dipole moment is found present in that molecule. So this is a micro inactive molecule. So it does not show the radial rotation spectroscope. And this lastly, a symmetrical top molecule. So where IA is not equal to IB, IB is not equal to IC. Now such type of the rotations are observed applying a certain moment of inertia. So these are the four types of the same in terms of like this is another way of showing in a colored picture. This is a spherical top molecule and symmetrical top molecule, asymmetrical top molecule. So now let us go for the study of expression for the moment of inertia. Let's derive an expression for the moment of inertia of diatomic molecule considering as a rigid rotator. Now let us consider a molecule having the different electronegativity atoms in that molecule, and this is a bigger molecule and the smaller molecule. This size, just observe size of this one. So this M1, M2 and A and B here now. Now let's consider AB is a diatomic polar molecule having a permanent dipole moment. M1 and M2 are the masses of A and B. R1 and R2 are the distance from its center of gravity when the molecule is rotated about its axis perpendicular to the nuclei of to the line joining between the nuclei of A and B. R0 is the total bond length of A and B. So just observe, this is the mass A is a mass 1 M1 and M2 is the mass of B, and this is a total distance from the nuclear of from one nuclear to other. This is the internuclear distance of the two atoms in the molecule, that is R0, and here this is being a center of gravity. See, the center of gravity will not rise exact middle because depends on the balancing of that molecule, where it balanced depends on the difference in the masses. Now this is a heavy molecule, this is a light molecule, then the center of gravity will not lies exactly middle of this, it lies somewhere near to the higher mass. Therefore this is the center of gravity. From the center of gravity to the M1, this is called R1. This is from the C2 up to the nucleus of M1, R1, and this is from C2 up to M2, this R2, and sum of the R0 is equal to R1 plus R2, this is total. Since since the molecule is considered as a rigid rotator, there is no change in the bond length and bond angle, hence the total moment of inertia AB molecule remains same, hence the system is equally balanced. That means here from the center of gravity M1 R1 is equal to M2, so M1 R1 is equal to M2 R2. Just for the rearrangement, for the further discussion, we shall go for some rearrangement here. Keep R2 here, keeping R2 and the M1 R1 upon M2, that you can call the equation 1, and keep R1 as it is here, M2 R2 divided by M1, you call this equation 2. Now the total moment of inertia of the diatomic molecule is given by, so I is equal to M1 R1 squared plus M2 R2 squared. So moment of inertia for a single atom, you can say m r square, but here the two atoms are there from the center of gravity. So the sum of the moment of inertia of both the atoms in a molecule is to be considered. So I is equal to m1 r1 square plus m2 r2 square. Now you just observe this m1 r1 square. You can split this r1 squared into as a r1 into r1. So m1 r1 r1. So from the previous relation, so m1 r1 is equal to m2 r2. So keeping m2 r2 and another r1 rise as it is here, plus you can split this r2 as a r2 into r2, and m2 r2 is equal to m1 r1 in r2. Now from this modified equation, that means substituted this m1 r1 is m2 r2 and r2 by means of m1 r1, and here now I is equal to r1 into r2, you take in common from this m1 plus m2, called equation 3. The total bond length of AB molecule is given by r0 is equal to r1 plus r2, we can call the equation 4. And by using equation 1, that means this is equation 1 here, equation 1 and 2, substitute this equation 1 and 2. So r0 is equal to r1 plus, you keep r2 m1 r1 divided by r2 and take out common r1 as a common from these two equations. So 1 plus m1 upon m2, just further you have simplified it now. At last r0 is equal to r1 m1 plus m2 divided by m2, or keep r1 as it is, r1 is equal to r0 into reverse of this m2 divided by m1 plus m2, this equation 5. Similarly, substitute the value of r1 from equation 2, we are getting another equation, r2 is equal to r0 m1 divided by m1 plus m2. So these are the equation number 6 here. So next substituting equation 5 and 6 in equation 3, just remember this is equation 3, I is equal to r1 r2 into m1 plus m2. We have the value of r1 r2 from just 5 and 6 equation. So here you can say r0 m2 divided by m1 plus m2 into r0 m1 divided by m1 plus m2 into this remains as it is and gets cancelled here. We left with this r0 squared here, m1 and m2 divided by m1 plus m2, and we can go for the replacement of this term by means of mu. I is equal to mu r0 squared. This equation known as a moment of inertia diatomic, consider the rigid rotator. So mu is nothing but a reduced mass. Now the entire the value m1 into m2 divided by m1 plus m2 is replaced by a word, that is a letter mu. Mu is a reduced mass. Okay? then I is equal to mu r0 squared is final equation of moment of inertia. From this one, we can go for the calculation of the mass of each atom, or also moment of inertia, and so we can also calculate what the internuclear distance, that is a bond length of the given molecule. So this type of equation used for the problem in calculating, this equation used to calculate the bond length, mass, and also moment of inertia of given molecule. So this derivation asked in the examination for 5 marks. So be prepared for this one. Okay, thank you.